This is worksheet 1 of the States of Matter packet, and this is the packet where we are going to look at sort of the biggest picture of all the things we've looked at so far. All right, we started off talking about individual atoms and the protons, electrons, and neutrons that make them up. Then we started talking about what happens when atoms combine together into different types of compounds and the bonds that hold them together. But now we're going to talk about, okay, once we have those individual molecules, all those compounds, and the units of compounds, which are molecules, right? How do all of those molecules act together? And so this is really a discussion of the 3 general states of matter, which you learned about on a really sort of basic level in previous science classes. So you've probably heard of the ideas of solids, liquids, and gases before. So in a solid, a liquid, or a gas, any of these states of matter, there are many molecules acting together. Right? And the way the molecules act is going to determine if that substance is a solid, a liquid, or a gas. And we can explain most of the way the molecules act and interact with each other by the intermolecular forces that hold them together. Okay, so these are not small-scale bonds that hold individual atoms together. These are forces outside of whole molecules that hold the molecules together, right? And they're not as strong as bonds, but relatively speaking, they're pretty strong. And you may have seen this before if you've ever taken a penny and tried to see how many drops of water you can fit onto the top of the penny. Sometimes they have you do that in middle school. And it's pretty impressive. You can fit lots and lots of drops of water on top of this penny. Why is that? Well, because there are these forces that hold the H2O molecules together and have them sort of act almost as one thing, as this liquid. So those are the kinds of things that we're going to be looking at in this packet. So hopefully this first worksheet is somewhat of a review with a little bit of new information added in, but I do want you to make your paper look as similar to mine as you can as we go through this. All right, so solids have both a fixed shape and a fixed volume. So what does that mean? Well, let's say that you have a big cardboard box, or we'll make this scientific, let's say you have a big glass beaker. Okay, so you have a big glass beaker and you put a solid cube into it, right? That solid cube is not going to change its shape, so it has a fixed shape. And it's not going to change its volume. It's not going to change the amount of space it takes up just because you put it into another container. And the reason that the solid doesn't change its shape or volume, depending on what you put it in, is because the intermolecular forces that hold together the molecules making up that solid are very strong. So the molecules can't really move far away from each other. The motion of the molecules is really small, so all the molecules really do is just sort of vibrate in one fixed location. And so I represented that, and I want you to do this too. Right here, I said, okay, let's say we've got this solid mass that's made up of, just to simplify, these 6 molecules. Okay, so these little circles here are representing individual molecules. And so when you put this mass inside of another container, so the square that's already on your worksheet is the other container, you can see that the solid doesn't change its shape to take the shape of the container, and it doesn't change its volume. It doesn't expand until it fills up the whole container. Okay? All right. So if we move on to our next state of matter, we have liquids. Okay, don't worry about the melting, freezing stuff yet. We'll get to that in a minute. Liquids have a fixed volume, so they're not going to change the amount of the amount of space they take up depending on what container you put them in. So they have that in common with the solids. But their shape can change, right? So if you pour water from a graduated cylinder that's tall and skinny into a beaker that's round and fatter, then the liquid is going to change from having the shape of the graduated cylinder to having the shape of the beaker, right? And the reason that they can change shape, these liquids, is because their intermolecular forces are not as strong as they are in a solid. And so the molecules aren't on such a tight leash. They can sort of slip and slide a little bit past each other, and this is what allows liquids to do what we describe as flowing. right? So with a solid, it's not going to flow. If you have an ice cube in a graduated cylinder and you go to pour it into a beaker, it's not going to flow. It's just going to sort of plop in there. But with a liquid, it's going to flow. It's going to move all together as one unit. And this is because the intermolecular forces are not quite as strong. Okay, and then the last state of matter that we will talk about in this class is a gas. And gases do not have a fixed shape, and they also do not have a fixed volume. All right, there's kind of nothing consistent about them. So if you open a bottle of perfume, right, the liquid that's in the bottle of perfume starts to evaporate right away, and it's releasing these gas molecules into the air. And if you're standing on one side of a classroom, so the classroom is your container in this case, right, sort of a large container. If you're standing in one corner of a classroom, the people right around you are going to be the first ones to smell that perfume because those gas molecules are starting to expand and move to fill the container, the classroom. And if you wait long enough and you have enough perfume, eventually somebody even on the opposite side of the classroom is going to be able to smell that perfume. Why? Because the gas molecules have expanded all the way to all the outer edges of the classroom. They'll keep expanding until they take up the entire container that they're in. Right? So that's why I'm showing the individual molecules here sort of expanding until there's spaces between them, but they've pretty much covered that whole container. All right, so these molecules are moving about freely, and they expand to fill any container they're in. All right. So the other thing we have to talk about here is how molecules can change their state of matter. Okay, and we have a term for that. It's called a phase change. It's going to be an important term for you in this unit. So a phase change is when a material changes from one state of matter to another. So it could be from a solid to a liquid, from a liquid to a gas, all different options there. Right? But the important thing to remember is this is not actually changing the atoms that are bonded to each other in the molecules. Okay, so this is a physical change. It's not a chemical change. And I'm going to use an example that we're mostly familiar with, right? So we'll use the example of H2O molecules. Okay? If you start off with, let's say, an ice cube, right? In an ice cube, you're going to have all these H2O molecules, and they're going to be packed super close together. Okay, and they're not able to move very much. They're really tightly packed in this ice cube. Okay, now if you want to change that ice cube into liquid water, what do you have to do? Well, you have to add energy. Right? Now, we think of that as adding heat because heat is a type of energy. So, yeah, that's the type of energy you're going to add, right? So, you take the ice cube out of the freezer. So, you're adding some heat energy in the room, okay? And all of a sudden, these H2O molecules start to move a little further apart. Okay, they're still relatively close together, but they're not crammed quite as close together. Okay? 1, 2, 3, 4, 5. Oh, I'm supposed to have 5 of them. Okay, there they are. But do you notice that you still have 2 hydrogens bonded to each oxygen, right? If I were to change that and I were just combined a bunch of hydrogens together and a bunch of oxygens together, like separating out the hydrogens and the oxygens, right, that would be a chemical change, rearranging how the atoms are actually bonded to each other inside a molecule. That's not what's happening in a phase change. Okay, now if I want to take this even one step further and I want to take that liquid water, I want to turn it into water vapor, or what we might call steam, I'm going to have to add some more energy, right? Like I might have to put my liquid water into a pan on the stovetop, turn the stove on. I'm adding more heat energy to the system. And by adding more energy, right, we're going to give those molecules even more freedom. They're going to move even further apart, and they're going to expand, and they're going to take up a whole bunch of room up above the stovetop. Right? And now we have a gas. But again, it's a physical change. I'm just moving the molecules further apart. I'm not actually separating which atoms are bonded to each other. I started off with H2O molecules. I moved into H2O molecules in the liquid, and I still ended up with H2O molecules by the time I got to the gas. All right, so that's a really important difference. They're all made up of H2O. I'm not actually changing the bonds within the individual molecules. Okay, now let's talk about this business of adding or removing energy from the system. right? We can group all of our different phase changes, our conversions between different states of matter, into two categories. All right, so the ones that require adding energy, which we can think of as heat, because that's really the type of energy we're talking about here. Oops, sorry about that. We can think of those as the ones that I have in red. So if you want to go from a solid to a liquid, if we think of like ice to liquid water, that's kind of easy, right? We call that phase change melting. That requires adding heat. Then to go, like we talked about, from our liquid to our gas, right, that's evaporation. That also requires adding energy. And one that we might be less familiar with is if we want to go, sometimes we can go directly from a solid to a gas. Okay, so dry ice is an example of this, right? So if you've ever been to like a Halloween party where they have like a witch's potion and it's like all this, it looks like steam coming off of it, right? What they did is they put a chunk of solid CO2, carbon dioxide, into the brew, into the witch's potion. And it's actually doing something called subliming, where it's skipping the liquid state. It's going directly from a solid to a gas. And carbon dioxide is kind of unique because it does that at room temperature, which is cool. Okay, but all three of those we can group together as requiring adding energy to the system. Now, the opposite of that, right, if you want to go the opposite direction, you've got to remove energy from the system. So basically cool things down, remove heat. Okay, so to go from a gas to a liquid, that's called condensation. Right, so like if you have a glass of water on a hot day and you're sitting outside and all of a sudden you get your glass, we say it's like sweating, right? Well, it's not really sweating, okay, that's what animals do, but what it's actually doing is those gases are hitting that cold glass, so the water that's evaporated in the air, if it's humid out, is hitting that cold glass and they're slowing down, removing heat from the system, then they're condensing into a liquid on the glass. Right? And then again, if we want to keep going, to go from a liquid to a solid, right? So if you have liquid water, you want to make ice cubes, what do? Well, you stick it in the freezer, remove some heat. That's called freezing. Okay? And then another thing that might be less common, maybe you haven't heard of, but you can go kind of the opposite of sublimation. If you want to go directly from a gas to a solid, that's called deposition. Okay, and there's not like great real life examples of this that we see. If you think back to earth science, there were sometimes explanations of how certain rocks would form, and they form by deposition. So there's elements in the air that go directly from a gas to a solid, and you get formation of specific rocks. So that kind of sums up this. What your next task is going to be is to use the information on this page to create a Venn diagram, and you're going to compare solids, liquids, and gases. All right, so for example, on your Venn diagram, you could say that both solids and liquids have a fixed volume, right? So that would be something they have in common. But something that they don't have in common, solids have a fixed shape and liquids have a shape that can change. Right, so I want you to try to pick as many of those things out and fill in as many of the bullet points as you can on the Venn diagram on the next page.